Can you all hear me and see the slides? Can you see the slides? Can somebody give me a confirmation?
Yes,
okay.
sir, we can.
Okay, great. So this is where I stopped last time, right? I talked about the 7 layers in the, that partition the overall job of networking, right? So starting from the bottom, we have a physical layer, transfers bits across a direct link. Direct link means from node A to node B, where these two nodes are connected by a link. That is, you do not have to go through intermediate nodes, right? And the data link layer transfers frames, which are nothing but a group of bits, across a direct link, but does so reliably as well. That means recovers from any errors that may happen. In the network layer, it transfers packets from a host. Host is an end node that is part of not a network node. So it's a computer or other end device, like a smartphone or other end device, right, to another. And it's responsible for addressing and routing and forwarding. And then transport layer transfers data from a process or a program application in a host or computer to a process in another host. And then we have the session, presentation, and application layer that are often combined together, and they do application-specific functions such as email, web, and so on, right? So I'm going to start with the physical layer, the bottommost layer. So that's responsible for transferring bits from one node to another node over a single link, right? How do you transfer bits? So there are only 2 kinds of bits, 1 and a 0 bit. So how do you transfer 1 or a 0 bit from one node to another node, right? So before I get to that, what is the benefit of digital networks? So if you have a digital network, then you can have all kinds of applications that are running over the network, right? So you can have email, telephone, voice over IP. You've heard about these things. Digital video, all of this are enabled by the single network. That's because it can transmit bits. And when you convert any signal into bits, then basically you're transmitting that signal over that network, right? So what is the benefit of digital network or digital transmission over analog transmission? So this is a simple figure that shows you the advantage of digital transmission over analog transmission. Now, if it's analog transmission, basically you're transmitting some kind of an analog waveform. That means a waveform that varies continuously, can take any voltage value, for example, at any time, right? That's an analog signal. So for example, you see the cursor that I am pointing at. So this is an analog signal that a transmitter is sending. When you transmit a signal over a link, then the signal undergoes several impairments. Okay, it becomes basically, it changes shape and it becomes weaker. So this is distortion and attenuation. Distortion means it changes shape. Attenuation means it becomes weaker. That means its amplitude decreases, right? So the receiver might receive a signal that looks like this, which looks very different from this, right? So the difference between these two can be thought of as error, right? It's noise or error, the effect of noise or error between these two. Now, on the other hand, digital transmission, you only need to transmit discrete levels. For example, a positive pulse for a 1 bit and a negative pulse for a 0 bit, or a positive pulse for a 1 bit and no pulse for a 0 bit. You only need 2 different distinct symbols that you want to transmit. So if your waveform is this, for example, you transmit a positive pulse for a 1 bit and a negative pulse for a 0 bit, the receiver might get something like this because of distortion and attenuation. But still, notice that the receiver is not making any errors in terms of recovering the 1s and 0s, because the receiver sees a positive pulse here and therefore recognizes that, oh, this must be a 1 bit and this must be a 0 bit. So even if there are these impairments, distortion and attenuation, it's possible for the receiver to recover the bits exactly. That doesn't mean that always happens correctly. For example, if it's so distorted that this positive pulse becomes a negative pulse, if there is some noise that the positive pulse becomes a negative pulse, then this bit is going to be interpreted as a 0 bit instead of a 1 bit that was transmitted. Right? So errors are still possible, but the probability of these errors is reduced by a great deal when you are transmitting bits as opposed to transmitting analog signals. Okay, does that make sense? Okay. So that's why we use digital transmission. Right now, fine. So digital transmission has its benefits, but is all of the information that's generated that you want to transmit in digital form? Okay. That's not necessarily the case. In a computer, of course, the form of the data is digital. Okay, because that's what the computer generates. It's going to generate bits, ones and zeros, because that's what it uses to function, right? But not all information that is generated is digital in nature. For example, if I have a microphone, then it's going to produce an electrical signal, right, from the voice signal, and that electrical signal is going to be an analog signal. Right? That's not a digital signal; it's an analog signal. Similarly, if you take a video camera and start shooting a video, then that's going to be it's an analog signal, right? That's what it's produced naturally. So how do you convert that to a digital signal? Okay, so we need to do that if we want to transmit that over a network, right? Such as audio, right, and video. So all analog signals can be characterized by their bandwidth. Okay, this bandwidth is different from the bandwidth of my link. We say that this is 10 megabits per second, and that's not what I'm talking about here. I'm talking about the bandwidth of the signal. Okay, here it refers to the amount of frequencies or the spectral content that the analog signal has. Okay, and you can obtain this bandwidth with a Fourier transform. I'm not sure if you all know what that Fourier transform is, but basically it's a way of representing a signal, a waveform, as the summation, or to be more accurate, as an integral of sinusoidal signals, sine waves of varying frequencies of different amplitudes. That's what the Fourier transform is, right? And generally, if a signal varies quickly in the time domain, then it has a broader spectrum in the frequency domain. This figure right here shows the relationship between the time domain signal, which is the waveform, and the frequency domain signal, which is the spectrum, as we call it, right? So suppose we have a signal that looks like this, right? Looks like this. Now this waveform can be represented as the summation, or summation is not an accurate term. Summation means you have a number of discrete components. When you have infinite components, uncountable components, the correct term to use is integration, right? So here I'm just showing discrete things because it's not possible to represent infinite number of frequencies here. So here are 3 different sinusoidal sine waves, right, of different frequencies, as you can see here. And when I add these up and these and some more frequencies up, then this signal can be recreated when these are added up. So this spectrum right here shown in blue is basically tells us what frequency components, that is, what frequencies of these sine waves need to be added up to recreate this time domain signal, and what is the amplitude of those sine waves. That's what this spectrum is, right? So the bandwidth of a signal is basically the set of frequencies over which we have a sufficient amount of amplitude that should be added up to create the original signal. So there is very little power in the signal outside of the 2 frequencies, outside of a lower frequency and a higher frequency. So the difference between the higher frequency and the lower frequency then becomes the bandwidth, right? So to convert an analog signal to a digital signal, there are 2 steps that we use. Okay. So when analog signal, then that signal has a certain bandwidth, right? So here's an analog source. The first thing you do to convert it to a digital signal is do something called a sampling. Okay. Sampling means you take a sample of the waveform every once in a while in the time domain, right? So maybe you sample the waveform every 1 second, or every 1 millisecond, or every microsecond, so on, right? So if you sample it 1 millisecond, for example, millisecond is 1,000th of a second. So if you sample it 1 millisecond, then we say that the sampling rate is 1,000 hertz, right? 1,000 times per second, right? Because 1 millisecond is 1 over 1,000. So sampling rate now is 1,000 samples per second, right? So there is a theorem that states that if the bandwidth of the analog signal is W hertz, then the sampling rate has to be 2W samples per second. And you may be familiar with that. It's called Nyquist sampling, right? 2W samples per second. So if you take samples of this analog signal 2W times every second, then Nyquist showed that it is possible to, using these samples, it's possible to recreate the analog signal exactly. Okay, so it's a beautiful theorem that Nyquist proved, that if you can sample this at this rate, then you can recreate the analog signal exactly. It's not an approximation, it's an exactly. But these samples now give you basically real voltage values. Let's say this is a voltage signal, right? So you get real values, which means one of the samples could be 2.345 volts. Another one could be pi volts, right? I'm just giving an example. So there could be arbitrary real numbers, okay? But then how do you represent these arbitrary real numbers in ones and zeros? We know that when we are representing numbers using bits, ones and zeros, the precision is going to be limited, right? We have room only for so many bits, okay? Just like in programming, you have integer variable or a double variable, but the precision is only so much, as many bits that you have, right? So how do you represent this arbitrary real value using bits? Well, we cannot do that. So we do an additional step called as quantization. So what we do in quantization is, suppose we have a voltage value of pi volts as one of the sample values. Pi, of course, as you know, has an infinite number of digits, right? It goes on, it's never ending, it's an irrational number, right? So it cannot be represented with a finite number of bits. So instead, what we do is we approximate it. We say, I'm not going to do 3.14159, etc. Instead, I'm going to approximate it by, let's say, 3.2. Okay. So when you approximate it like this, you have a finite number of levels, right? So that's called as quantization. So you say maybe every 10th of a volt. So you say 3.1, 3.2, 3.3, 3.4. These are your levels, and you're going to approximate the sample value by the closest level. So when you have a discrete number of levels, it's possible to code that using bits. For example, if you have 8 levels, then you can represent that using 3 bits, right? So with 3 bits, you can represent 8 different combinations, 0, 0, 0 to 1, 1, 1. So you can represent using with powers of 2. So if you have 256 levels, 2 to the power 8 is 256. So you can represent that any level with an 8-bit string, right? So these two steps together allow us to convert an analog signal, any analog signal represented as a string of bits, right? So that's how you convert an analog signal to a digital signal. Then once you've converted to a digital signal, you can either transmit that over a network. If you have a digital network, you can transmit that over a network, or you can store it for later retrieval. You know where we store things? CD. You're all familiar with the CD, right? I don't know if you're still using CDs because everything is now in MP3. Audio is all in MP3 now, but that's what you do in MP3 as well. MP3 is digital music, right? So you do sampling and quantization. Now you have ones and zeros. You can store it as an MP3 file, okay? Or store it on a compact disc, right? Or you can transfer it over a network. And the receiver does the opposite process. It recreates the analog signal from the digital data that is either stored or received. Okay. So in the case of a CD, for example, the CD player is going to do this process. It's going to recover the music, which is the analog signal. Right? This shows the quantization process. So that's too much detail. So let me skip that. Okay. So now we know how to convert an analog signal to a digital signal. Now the physical layer is responsible for transferring those bits. Okay. So bits have to be converted into pulses. Okay. You have a 1 bit and a 0 bit. You have to transmit them. And as I showed you earlier, these bits are going to be converted to pulses. A positive pulse for a 1 bit and a negative pulse for a 0 bit, for example. Right? So that's how you do it. And this is exactly the job of a communications engineer. So the communications engineer's sole job is really to figure out how to transmit bits over a link or a channel, okay, or a transmission medium. So here are some questions that a communications engineer grapples with. How fast can you transmit, okay, these pulses? That is, how closely can these pulses can be spaced? If the pulse width is 1 microsecond, that means you can transmit 1 million pulses per second. And if you're transmitting 1 bit with 1 pulse, then that means you're transmitting at 1 megabit per second. Right? Now, it is possible actually to transmit more than 1 bit with a single pulse, because the pulse doesn't have to be just high or low. It could be, very high, high, low, very low. So now there are 4 different levels, right? So I can transmit 2 bits with this thing, because with 4 levels, I could encode 2 bits in 1 pulse, right? So it's possible to transmit multiple bits with a single pulse. And then the question is, how fast can you transmit these pulses? That is, how many pulses can you transmit in 1 second? How far can you transmit them? What is the distance of length of the link that you can transmit these pulses? Are they going to, retain their shape and level for a long period, for a long distance, or is it going to be distorted very quickly? How reliably can you transmit? Right? This is kind of related to the how far can you transmit, as well as how fast you can transmit as well. That is, can you transmit them without errors, right? And finally, of course, how cheaply can you transmit? Cost is always an important consideration, right? So you cannot say, I'm going to transmit a pulse with 1 gigawatt, okay? Because that means you cannot have that kind of a power coming out of a cell phone, right? So that's important as well. So this typically translates to power. Cost translates to power, right? So when you transmit these ones and bits, so here is a communication channel. So this is either a cable or it could be a wireless medium. For example, in Wi-Fi, you're transmitting this over radio. There's no wires, right? Okay. So when you transmit this, the signal undergoes many impairment, as I said, right? So look at the right-hand side here. So attenuation is the weakening of the signal. The signal becomes smaller in amplitude. Distortion, which means the signal changes shape. Then there is noise, external noise that affects the signal, as well as interference from other signals. Because this may not be the only signal that is being transmitted on a wire. There may be other signals, possibly in a different frequency, okay, in a different channel that is being transmitted, but on the same wire. So there could be some interference between those other signals. So all of these essentially limit how accurately you can measure a particular value of a signal at the receiver, right? So if the impairments are very bad, then the receiver is going to make mistakes, and therefore the error rate is going to increase, right? So each channel or medium or cable can only transfer a band of frequencies. They cannot transfer everything that you transmit through them. They can only transfer a band of frequencies. That's called as a channel's pass band. Okay. For example, Wi-Fi, right? So the Wi-Fi channel, it's wireless. Okay. So that channel has a bandwidth of several hundred megahertz. Okay. And the actual frequencies at which the Wi-Fi operates is 5 gigahertz, also at 2.4 gigahertz. So there are 2 bands for Wi-Fi, right? But the bandwidth of the channel is several hundred megahertz. That's what you have. So if you transmit any signal that is outside of the channel's passband, then that signal will be blocked by the channel. For example, you cannot transmit an optical signal, that is with a laser, on a Wi-Fi channel, because Wi-Fi channel can only transmit radio waves, right? So similarly, you cannot transmit radio waves through optical fiber. Okay, that's not possible because you won't get any signal at the other end. So every transmission medium has a certain passband, and in order for you to use it for communication, use that medium for communication, whatever you're trying to transmit must fall within the channel's passband. Okay. Now, sometimes when a signal is generated, it may not naturally lie, may not natively lie within the channel's passband, right? For example, when we use a microphone to to get our voice signal, right? Convert our voice signal to an electrical signal, right? Now, the frequency of this is, we all know that our ears can distinguish frequencies only from 0 to 20 kilohertz, right? So anything outside our ears cannot hear it. And the same goes with voice as well. So when we speak, the signal is in that range, 0 to 20 kilohertz. 20 kilohertz is really the really high end, may not be producible by most humans, but could be done by, high-pitched instruments, for example, right? So this is in the 0 to 20 kilohertz range. Now, if you take it as it is and try to send it over a Wi-Fi channel, for example, you won't succeed, because Wi-Fi channel, its passband is here in the 5 gigahertz range. It's not in the kilohertz range. So if you directly transmit it, it's not going to succeed. That channel will simply block the signal. Okay. So what do? We do something called as modulation. So modulation is a process of basically converting the signal, such as the voice signal, right, into a signal that can be transmitted over a particular channel. If you want to transmit your voice signal over a Wi-Fi channel, then you have to modulate a carrier signal, okay, with the voice signal and transmit. And we are actually very familiar with this. You all know about AM and FM radio, right? What do AM and FM stand for? Amplitude modulation, frequency modulation. Okay, so that's what the modulation means, right? So when a radio station is transmitting, it's transmitting at a certain frequency range, and we tune our radio receiver to receive that radio station. Right? So that's how it works. So it's using modulation. Okay. So what I'm showing here is, so there are different kinds of signals that operate at different frequencies. So this shows the various frequency bands. So this here is 10 square. This is 10 to the power of 24. This is frequency at the top here. Okay, 10 square is 100 hertz, and 10 to the 24 is 1 with 24 zeros, big number, right? So this is the frequency. So different frequencies are used for different purposes. So you see, telephone is here in the 100 hertz range, and this is DSL. Cell phone is in the couple of 100 megahertz range. Wi-Fi is a little bit higher. 10 to the 10 hertz means 10 gigahertz roughly. Right, 5 gigahertz is what I mentioned. Optical fiber, it transmits signals in the terahertz range. So the optical fiber, you do not actually transmit visible light. You transmit ultraviolet light. Okay, so that's what you're transmitting here. So in wireless, there is a large frequency range which is amenable for wireless transmission, and we call this as radio spectrum. This is a pretty large frequency range in itself. Anything from 30 kilohertz to 300 gigahertz is called as radio. Okay, is radio different from a radio receiver that we're all talking about? This here we're talking about radio is the name that is given to the spectrum, the range of frequencies that can be transmitted wirelessly, right? So that's what it's called, radio. So this is in terms of frequency, this is 10 to the 4 hertz. So this is 10 kilohertz, right? 10 kilohertz, and this is a terahertz, right? So even within this radio spectrum, different bands, different frequency ranges are used for different purposes. For example, AM radio is here. FM radio is in the megahertz range. Microwave, you have heard of microwave. By the way, this microwave uses the exact same principle as the microwave appliance that we have in our homes to heat up food and stuff, right? Okay, so that's what the physical layer is about. Its physical layer is about how to transfer bits from one node to another node. And the bottom line is, you have to convert those ones and zeros into pulses that are then transmitted. And these pulses are going to change shape. We cannot do anything about it. The thing is, we still need to be able to recover the ones and zeros at the receiver side, even if they change shape. If they change shape too much, then that is going to introduce errors, and we have to figure out how to recover from those errors. So that means sometimes Very rarely, a 1 can be converted to a 0 and a 0 can be converted to 1, which we don't want to happen, right? So what do we do about it if an error happens? So that's where the data link layer comes in. Okay, so now the physical layer has taken care of the job of transmitting bits from one node to another node. How can we build on that to build a true network? So recall that the data link layer transfers frames. Frames are nothing but a group of bits. I gave you the example last time. Bits are like alphabets, right? Alphabets by themselves don't have any meaning. You have to put them together to create words, which have meaning. So just like that, bits by themselves don't have meaning. You have to put together bits to create meaning. Okay, so that's what I mean by frame. Okay? So when you transmit a frame, the frame is going to be transmitted bit by bit. Okay. So the data link layer is responsible for figuring out where a particular frame starts and where a particular frame ends. Just like when we are writing words, we can identify where one word ends and another word begins because we put a space. Okay. Same thing happens in talking. So you know that there is one word is different from another word because I'm kind of pausing a bit. I'm introducing this short pause. Right? So that's how you know that this is one word, that's the next word. But when you're transmitting ones and zeros as frames, how does the receiver know where a frame ends and where the next one begins? Right? So you could have pauses just like in written language or spoken language. You could have pauses, that is, you don't transmit any signal to identify that the frame has ended. Some channels, it turns out that you cannot do that. You always have to transmit something on the channel. Otherwise, the channel goes dead. The link dies. Okay. So in order to keep the link alive, you have to transmit something or the other all the time. So in that case, how do you distinguish how do you tell where the frame starts and where the frame ends? Okay. That's part of the data link layer. It puts in enough information there to figure out where a frame starts and where the frame ends. Okay, so this shows an example. So here is the information bits, and this is all some header information and trailer information. This is information that is sent by the data link layer protocol to the receiving side data link layer protocol to figure out what to do with the frame. Okay, so how do you figure out where the frame starts and ends? We have a flag at the start and end of the frame. The flag is nothing but a special bit pattern. For example, the bit pattern could be like this. This is 1 byte, 0, 6 ones, and a 0. So that's a flag. That's a special pattern that indicates that this is the start of the frame. This is not part of the data. This is just the start of the frame. Similarly, when the frame ends, you put the same flag. Now, one of the challenges is, what if this flag data appears inside the information? The information can be anything, right? It can be any combination of ones and zeros. What can the receiver do if the flag appears in the information? So then if you don't do anything, then the receiver is going to think that this flag, if it appears inside the information, that's the end of the frame. And it'll make a mistake. It'll prematurely terminate that frame and say, okay, the frame is done. Whereas it's actually not done. Okay? So there are ways in which that can be, the transmitter can tell the receiver that this is not a flag. This is just user information. So there's a process called as bit stuffing, which I won't get into here. That is done by the transmitter to tell the receiver, this is not the end of the frame. The end of the frame is actually here. Okay. The second thing is errors, right? So one function of the data link layer is to identify the start of the frame and the end of the frame. The other important function is error control. What does that mean? It means that no matter how much care you take in your transmitter or receiver, some bits are going to be bad, which means there are going to be errors in some bits. Some ones are going to be changed to zeros, some zeros are going to be changed to 1. Of course, the receiver does not know which bits are changed, right? Because if it knows, then it can go and fix it. But it doesn't know. Okay. But then, is there a way to figure out that there is an error somewhere? Never mind fixing it. Is it possible to know that there is an error? What can you do if there is an error? If there is an error, then the receiver can send a message to the transmitter, say, resend that frame, retransmit that frame. Okay. So maybe when the frame is retransmitted, there is no error the next time, because most of the errors are due to temporary disturbances on the channel. Okay. Maybe there is a small glitch that caused some bits to be flipped. So the next time it's transmitted, maybe there's not going to be an error. If there's an error, then the receiver is going to detect that, and it's going to ask the transmitter to retransmit that frame one more time, and so on. Okay. But for this to work, the receiver must be able to figure out that there is an error in the frame. Okay. So how can the receiver tell that there is an error in the frame? The transmitter is transmitting a frame which consists of an arbitrary set of bits, because the information can be arbitrary, right? Transmitter is trying to send some information to the receiver. The information can be arbitrary, which means the bits are arbitrary. How can the receiver say that there is an error? Okay. So that seems to be a very hard question to answer. Fortunately, there are ways in which the receiver can detect that there is an error. Let me give you a simple example. Okay. So this type of error detection is called a single parity check. Okay. So here, suppose there are k information bits. Okay. Suppose the information bits are B1 through BK. So B1, B2, B3 to BK. Okay. So each of these B1, B2, etc. is either a 1 bit or a 0 bit. It's all binary data, right? Then we calculate a check bit. The transmitter calculates a check bit, so-called check bit, as follows. It adds up all of these bits and then does modulo 2. You know what modulo means? Modulo means you divide it by 2, and whatever the remainder is, that's modulo 2, right? So when you divide by 2, there's only 2 possible remainders, right? 0 or 1. Okay. So when you add up all of these bits and the sum is an even number, when you divide by 2, the remainder is going to be 0. If it's an odd number, the remainder is going to be 1. So there are only 2 possible values for the remainder. So the check bit is also that's why it's called a check bit, because it's a bit. It's a binary digit, right? Because the only possible values are a 0 or a 1. So then the transmitter forms what is called as a code word. The code word is nothing but the information bits along with the check bit. So you see the information bits here along with the check bit. Okay. So let me show you what this looks like with an example. So here's an example. So suppose this is 7-bit information, some random information bits. I'm taking 0, 1, 0, 1, 1, 0, 0. Now the check bit, which is also called as the parity bit in this case, is you add up all of those bits, 0 plus 1 plus 0 plus 1, etc. And the result is 3. So the check bit is 3 modulo 2. 3 is an odd number. So 3 modulo 2 is 1. So the red bit is the check bit. So the code word is formed by adding the check bit or attaching the check bit to the information bits like this. Right? Now the property of the code word is that it always has an even number of 1 bits. So if you look at it here, there are 3 1s in the information bits, and so the check bit is a 1. So there are four 1 bits in the code word. Right? So this is always a property of the code word in the case of the single parity check code. Okay. So the receiver, to detect an error, all it does is it checks if the code word has an even number of 1 bits. If there is no even number of 1 bits, then it knows that there is an error. That doesn't mean that if it sees an even number of 1 bits, there is no error. It is possible for 2 errors to happen. Let me show you an example here. So this is what the transmitter is going to transmit. So this transmits this frame. Suppose there is an error, single error in this 3rd bit, like this, the purple bit, right? Then the receiver notices that 1, 2, 3, 4, there are 5 1 bits. Therefore, this cannot be the code word, cannot be a code word. So it automatically knows that there is an error. It doesn't know where the error is. It sees 5 1 bits in the code word and says that there must be an error. On the other hand, if there are two errors that occur, for example, bits 3 and bit 5. So bit 3 changes from 0 to 1, and bit 5 changes from 1 to 0, like this. Then the receivers, remember the receiver is going to check for errors by simply counting the number of 1 bits. So it counts the number of 1 bits and finds there are 4 1 bits. That's an even number. So the receiver thinks that there is no error. But what has happened actually? There are 2 bits that are flipped. That's unfortunate, right? 2 bits that are flipped. So in this case, the receiver is unable to detect this error. Okay. So this simple coding scheme can detect all odd number of errors, but cannot detect any even number of errors. So all odd number of errors. That means if there is 1 error, 3 errors, 5 errors, etc., those can be detected. But all even number of errors, 2, 4, 6, 8, those cannot be detected. Okay, but this is a very simple code. So in practice, it's the same idea that is used, not simply parity check, but the idea of generating some check bits. But very sophisticated methods are used to generate these check bits to help the receiver to detect errors. Okay. You may have heard the term CRC, called cyclic redundancy check. So that's a very popular method for detecting errors. So lots of protocols on the internet use a CRC mechanism for error detection. Okay. So that's what the data link layer does, right? So it does frame, puts bits together called frame, and identifies the start and end of the frame and detects errors. Okay. Now, sometimes we don't use a channel for just communicating between 2 nodes. Sometimes the channel is shared. For example, Wi-Fi, it is not just 2 nodes. There is not a single transmitter and a single receiver. If you have a Wi-Fi access point, then lots of people can access that Wi-Fi access point, right? So this is a shared channel. It's a broadcast channel, right? It's not just a single point to a single point, but you have multiple sources in this case. Yeah, number of users that are using the same Wi-Fi channel, right? So in this case, there is a necessity to use something called as a medium access control protocol. So a protocol that controls how the shared medium has to be accessed by the multiple users that are sharing the channel. The medium access control protocol. There are lots of medium access control protocol. One simple way is if you have a channel that has to be shared between multiple users, you can simply say if there are 10 users, for example, hey, you 10 guys are going to share this channel. I'm going to divide this channel into 10 pieces, and each of you get a small portion of the channel. Okay. By the way, that's what happens in broadcast radio, for example, right? Because each radio station is broadcasting on a separate frequency, on a separate channel. So that's how the different radio stations are not interfering with each other. Okay. You can select what you want by tuning your radio receiver to the appropriate radio station. That is, you're tuning your receiver to that particular frequency. Okay, but they're all transmitting over the air. Okay, how are we able to listen to specific radio stations? Because they're transmitting on different frequency bands. Okay, so that's an example of this method called a static channelization. When a radio station wants to start up, it's given a specific frequency band. That's what it has to transmit on. It cannot change it. If it changes it, then it might interfere with some other radio station. Okay? Now, in the case of a computer network, it turns out that that is not very efficient because sources may be idle or have nothing to transmit for a long period of time and then suddenly transmit something. Unlike radio stations, which are transmitting some program, broadcasting some program throughout the day, right? So unlike that in computer networks, this is not very efficient, statically dividing this channel. So there are other methods of doing this. Scheduling is one method. Random access is another method. Okay. So I won't go into the details of that. So by the way, this channelization or fixed allocation is also used in cellular communication. So when you make a call, you go to the cell tower here, and you're allocated a pair of frequencies. So one for the uplink, that is from your phone to the base station, and the other one from the cell tower to your phone. And similarly for the destination, the number that you're calling, right? So a total of 4 frequencies are allocated, one for you, 2 frequencies for you, and 2 frequencies for the other person that you're calling. Okay. There is also a scheme called as random access, where nodes can transmit data whenever they want to transmit. But in a shared channel, if that happens, then it's possible that 2 nodes may transmit at the same time. They just happen to transmit at the same time, and therefore their transmissions will collide on the channel. Collide means their signals are getting mixed up. Therefore, the receiver cannot receive either of the signals from either of the transmissions, right? So in this case, the nodes will have to retransmit their frames at a later time. Okay. It is also possible for a controller to allocate the channel as needed. Okay? And there are again various methods for doing this. So there's a controller is basically asking all of the users, do you want the channel? Do you want to transmit something on the channel or not? If a user says, no, I don't have anything to transmit now, then that user will not be given access to the channel. If some other user says, yes, I need to transmit something, then the controller will give access only to that user for a particular time. So the user can transmit at that time in a non-interfering manner. Okay? So these are all methods to improve this scheduling. Okay. So I'll skip all of the details here. Okay. So the shared medium is used a lot in these types of networks called as local area networks or LANs. Right? You've all heard of this term LAN. Right? LAN stands for local area network, and they typically use a shared medium, which means that there's an underlying medium access control protocol that is coordinating how different users are transmitting over the LAN. Okay. For example, Wi-Fi, that's a LAN, right? So there is a control protocol that is running that is telling each of the users use this frequency channel, okay? And you use this frequency channel that is non-interfering, okay? And this is done dynamically. That means this is done on an as-needed basis. If your device has something to transmit, then you'll be allocated a channel. If your device does not have anything to transmit, if I'm not transmitting anything from my phone at this time, then I'm not going to be given a channel to transmit. Right? So that's how it works. Okay. There are the LAN protocols need to deal with a lot of complex things because machines or devices that are on LAN are constantly moved from one LAN to another LAN. Right? We do that all the time. You're sitting in the library or maybe connected to the library's access point at one time. And later on, you move to the cafeteria and then you're accessing Wi-Fi from there or from your department lab and so on. So you're basically moving from one LAN to another LAN, and you're not telling anybody when you're doing this, right? You go there and you connect to Wi-Fi and just automatically it works, right? How does that happen? Well, there is a protocol that keeps track of where you are, that keeps track of these changes, that you're not in this LAN anymore and you're in this other LAN, and then, figures that out and gives you access to the right place. Okay. So one of the very popular LANs is called as Ethernet. Okay. You may have heard of this because your computer probably has an Ethernet port. Okay, this is a wired LAN thing, and this is how it would look like. For example, this is a computer. You have a card that is inside your computer, an Ethernet card. It has an Ethernet processor that's shown here, and it's connected to an Ethernet network. And there are multiple devices. For example, here's a printer. This is a data server, etc., that are connected to the Ethernet network. And this is a shared medium. You have a single cable. All the nodes can transmit at the same time on the cable, but the Ethernet protocol, Ethernet MAC protocol, ensures that this can be done without any conflicts. Okay. So I'm going to stop today at this point because it's 12:50. So I've covered the physical layer and the data link layers. The physical layer transfers bits. Data link layer transfers frames in a reliable manner, right? Frames over a direct link, that is from one node to another node without going through intermediate nodes. Now the network layer is going to really make this a true network, that is by going through intermediate nodes, by going through switches, because so far we're not considering switches. We're simply saying, how do you send a bunch of bits from one node to another node, which are directly connected. Okay. What if the source and the destination are not directly connected? Like you have to go through intermediate switches. That's the job of the network layer. And that's what we'll talk about in the next class. Any questions? No questions? You shouldn't be so shy. You should be asking questions. So if not today, maybe you can prepare some questions for the next class. Okay. So it is pretty late now. It must be what, 10?
We have 8 minutes.
8, oh, we have 8 minutes. Okay. So 10, it must be close to 10:30 there, right?
Mhm.
Any questions?
If they have had this before and this is a refresher, they should have a lot of questions. Don't
They
you
should
think?
have a lot of questions, unless
Uh,
it's completely clear they know everything, all the concepts by now.
you can
Which,
type in the chat any question you have.
yeah.
Yeah.
Okay, well, maybe I can get to know the students a little bit more. I heard from a few students, Samhita, Ishwarya, and one other student. I haven't heard from the other students. So how about you introduce yourself? Because you have a few students here. Let me call names here and what I see. Vriksha. Just tell me your branch and what year you're in. Is Vriksha here? Okay, maybe not. Shruti?
I'm from the computer science department.
Okay, third year?
Yep.
All of you are in third year. Bhavya? Okay, I think all of you are in the third year. Just say your branch then. Bhavya?
I'm in the computer science department as well.
Right. Everybody's in computer science. Jumana? Jumana? It's not here. Divyashri?
Hello, sir. I am also from the computer science department.
Science. And Sai? Is Sai here? ECE department. Okay, okay. So we have mostly computer science, one ECE. Okay. So I guess computer science students, you've had this class before. I don't know if the ECE student also has had this class before, networking. But if you have, then this is a review or a refresher for you. Okay. Now we have two more classes on this. I will complete the network layer and the data link layer after this. And then I'll talk a little bit about some other types of network as well. And then Professor Bhuvana will talk about a specific kind of wireless network called LoRa. Okay. Okay, so I'll see you all next week. Come prepared with some questions.
Yes, sir. Thank you so much.
Bye.
Thank you, Suresh. Thanks
Bye.
for
Bye, Shanta.
spending your time with the students. Bye-bye.
Bye.
Thank you, ma'am. Thank you, sir.